Welcome to this deep dive, where we're tackling a really interesting paper, The Art of Scaling Reinforcement Learning Compute for LLMs. Now, if you're in the AI space, you know scaling LLMs for pre-training, well, it almost become a science.
Right, there are predictable laws there.
Exactly. But that crucial fine-tuning step, reinforcement learning, or RL, that's a different story.
Yeah, totally. That's the core problem they're hitting here. While pre-training scales predictably, RL fine-tuning has been this, major bottleneck. It requires just massive amounts of compute, often kind of wasted, frankly, because nobody had a solid way to predict how performance would grow. It was a bit chaotic.
Pure chaos, yeah. So the solution they propose here, it isn't just another new RL algorithm. They actually introduce a unified framework, a principled one. They map RL performance specifically. They use pass rate against GPU hours, but using a sigmoidal curve.
And this sigmoidal framework, it defines these two fundamental forces in scaling RL. It gives you $, which is the asymptotic performance ceiling. Think of it as the absolute best your current setup can ever achieve, no matter how much compute you pour in.
The hard limit.
The hard limit. And then there's by $, the scaling exponent. That tells you about compute efficiency, how fast you actually get to that ceiling, $.
Okay, so $, is like the top speed of your car, and by $, is how good the acceleration is. Is that a fair analogy?
Yeah, that works pretty well. And what they found is that most tweaks people were making, they only really affected by $, the acceleration. These authors figured out which knobs actually upgrade the engine itself, to raise that top speed, $.
And they didn't just theorize this. They backed it up with a ton of experiments.
Oh, yeah. Massive ablation studies. We're talking over 400,000 GPU hours spent testing things out.
Wow.
And through that, they validated this best practice recipe they call ScaleRL. And ScaleRL scaled predictably, all the way up to 100,000 GPU hours, setting a new state-of-the-art performance level in their tests.
Okay, so the biggest takeaway, the big revelation, seems to be identifying those A-movers, the things that actually shift the ceiling. And it turns out, it's only a few key choices.
That's right. Things like the specific loss type you use, the numerical precision like FP32 we'll get into, and just the sheer scale of the model. Those are the things that fundamentally change $. Most other stuff, it just changes the efficiency.
All right, so our mission today is to unpack how they built this ScaleRL recipe piece by piece and really understand how this predictive framework finally brings some scientific rigor to scaling RL. Let's dive in.
Sounds good. And, before this paper, the scale of RL training was getting, frankly, astronomical.
Yeah. Give us a sense of that scale.
Well, think about projects like DeepSeek R10. They apparently used 100,000 H800 GPU hours just for the RL fine-tuning part.
Just RL, wow.
Yeah, and that represents something like a 10x compute jump between LLM generations for that stage. But it was happening without any real scientific guidance. People were kind of relying on hope, ad hoc tweaks.
Flying blind, basically.
Pretty much.
So how did they brace some order to this? You mentioned the sigmoid curve. Why not just use the same power law scaling models that work so well for pre-training? Where did those fall down for RL?
Yeah, that's a great question. The fascinating thing is the math had to change because the metric itself is different. It's bounded.
Oh, okay.
Pre-training often looks at things like loss reduction, which can theoretically keep going down. It sort of fits that power law idea of unbounded improvement. But RL, you're usually optimizing for things like accuracy or pass rate in this paper's case.
Which can't go above 100% or 1.0.
Exactly. They're naturally capped. So trying to fit an unbounded power law model to a metric that is bounded, doesn't really work reliably in practice.
What happened when they tried it? Did it just give weird results?
Yeah, it proved pretty unreliable. For instance, they showed that when they tried modeling their 8 billion parameter-dense model data with a power law, it predicted an asymptotic ceiling other 1.0, like perfect performance.
Which is obviously not realistic.
Right. The actual performance they observed saturated much lower, somewhere around 0.65 pass rate. The sigmoidal curve, because it inherently saturates, it matched with reality much better and gave accurate extrapolations across different scales. That's what gives it the predictive power. Okay,
so the sigmoid model basically says performance will rise, then it'll level off at some maximum point, $, and the shape of that rise is governed by $, the efficiency, and $, which is just how much compute it takes to get halfway to that ceiling $.
Correct. Those are the key parameters. $, the ceiling, the steepness or efficiency, and C to the halfway point in terms of compute.
And they were careful about how they fit these curves, right? To avoid just fitting noise.
Absolutely. They set up a pretty rigorous fitting procedure. They only fit the curves using data from an in-distribution validation set of 1,000 held-out prompts. And crucially, they ignored the very beginning of training, like the first 1,500 GPU hours or so.
Why is that?
Because that early phase is often really noisy and chaotic. It doesn't reflect the stable, large-scale behavior they wanted to predict. So cutting that out gave them more stable and reliable fits for extrapolation.
Makes sense. So, okay, framework established, fitting procedure nailed down. Now the real detective work begins. Finding those A-movers, the things that actually lift the performance ceiling. Where did they start looking?
They began by looking right at the core RL algorithm itself, specifically the asynchronous setup, how the data flows between generation and training, because that really governs stability and efficiency.
And what were they comparing?
They compared the sort of standard approach, PPO off-policy T, which is used in quite a few places, against a newer streaming method called pipeline RLK.
Pipeline or RG.
Yeah.
Sounds efficient. What was the key difference in practice?
Well, the main thing is reduced latency. Pipeline RL works in this continuous streaming way. Generators send data, trainers process it, models get updated almost constantly. PPO can have more waiting time built in.
Okay, and did it raise the ceiling overall?
Interestingly, no, not directly. Pipeline RL 8, the version they settled on, it achieved a similar ultimate performance ceiling, a similar 8 compared to their PPO baseline. But, and this is crucial, it's dramatically improved the compute efficiency by the dollars. It got to that ceiling much, much faster because it minimized idle time and kept the training closer to the sort of ideal on-policy regime. So it was more of an engineering win that accelerated progress towards $.
Got it. So Pipeline RL makes you faster, but doesn't necessarily make the car's top speed higher. Next up, something that did seem to raise the top speed.
Yeah.
The loss function. They started with DAPIO, but ended up choosing CISPO. What's the difference there?
Right. This is a big one for dollars. So DAPIO, the baseline, uses what's called asymmetric clipping, CISPO, which stands for Truncated Importance Sampling Policy Gradient. It also manages how far the new policy update can stray from the old one, but it uses a specific sort of truncated method to handle samples that might have really high variance.
Okay, a different way of calculating the policy update and the impact.
The impact was significant. Yeah, stunning is a good word. CSPO and another one they tested called GSPO, they substantially boosted that asymptotic pass rate $8. The DSPO baseline seemed to consistently hit a ceiling around $1 at 0.5 times 2 levels.
Okay.
But CSPO consistently reached $1 at 0.5955 in the same setup. That is a huge lift in the actual maximum capability the model could reach.
Wow, yeah, that's a big jump. And why CSPO over GSPO then?
Robustness, mainly. They found CSPO was highly insensitive to the exact choice of its clipping hyperparameter. You could tweak it quite a bit, and a $1 stayed high. DSPO, on the other hand, was extremely sensitive. Get that clipping value wrong, and your ceiling dollars could just plummet, so CSPO was safer, more stable.
Stability seems like a recurring theme here.
Yeah.
Which brings us to that weird fix you mentioned earlier, the FP32 precision thing. That wasn't even about the algorithm, right? It was like a systems issue.
Exactly. This is one of those little technical gremlins that can completely derail huge training runs. The problem was basically numerical instability. Tiny, tiny differences, mismatches, between how the inference kernel, the part generating text, and the training kernel, the part calculating updates, handled the numbers. Especially right at the language model head, where the final logits are produced.
So like rounding errors accumulating or something.
Sort of, yeah. Differences in floating point arithmetic between the two processes were causing instability during the RL updates.
And the fix was just use higher precision.
Pretty much. Switching the LM head calculations, specifically the logits, to use FP32 precision standard 32-bit floating point for both the generator and the trainer, that solved it.
Huh. Simple fix, big impact.
Massive impact on RLer. This seemingly small change boosted the ceiling from around 0.52 up to 0.61 in their base experiments. And they noted this fix was absolutely essential when they started scaling up to really large models, especially the mixture of experts ones. It prevented numerical blowups that would otherwise force the performance to plateau way too early.
Okay, so the core of ScaleRL is taking shape. We've got Pipeline RL for speed, CSPO for a high and stable ceiling, and FP32 precision to keep the numbers clean. These are the big A movers, or things that enable A.
What about polishing the recipe? Tuning the efficiency parameters $80 and shaded well.
Right, so the final ScaleRL recipe bundles these A-focused components with several other techniques specifically chosen to optimize efficiency and stability, B optimizers, essentially.
Like what?
Things like how you aggregate the loss across a prompt they found. Prompt level averaging worked best. how you normalize advantages, batch level normalization was adopted,
Mm-hmm.
and then a couple of clever data filtering techniques.
Yeah, I wanted to ask about those. Zero variance filtering and no positive resampling. They sound interesting. What do they do?
They're basically smart ways to manage the training data during the run. Zero variance filtering is simple. If you have a prompt where the model generated several different responses, but they all got the exact same reward.
Meaning there's no signal about which response was better. Exactly. There's zero difference, zero advantage. So trying to compute a policy gradient from that prompt is pointless. It just adds noise or wastes compute. So they filter those prompts out of the batch.
Okay, makes sense. And did that help?
It did. It gave a small boost to both efficiency and the final ceiling of dollars, raising it slightly from 0.520 to 0.540 in one comparison. So cleaning up the data helped stability and performance.
Removing the junk data, basically. What about no positive resampling?
That one's more about curriculum learning, focusing the model on harder examples. It permanently removes prompts from the training pool once the model consistently solves them, say, achieves a pass rate of 90% or higher on that specific prompt over time.
So stop practicing the easy stuff.
Precisely. The idea is to ensure the model spends its limited compute cycles tackling the challenging prompts where it still has room to improve. This improves scalability and also seemed to contribute to a higher overall ceiling of dollars.
This whole process sounds incredibly meticulous, all these components interacting. Did they do anything to confirm the whole recipe worked well together? Like, what if removing one small piece actually breaks everything?
Yeah, they did exactly that with leave one out or LRO validation. It must have been nerve-wracking, like you said. They'd take the full ScaleRL recipe and then intentionally remove one key component at a time and rerun the training.
And what did they find?
Well, the results basically reinforced their choices. Even when they pulled out one of the efficiency components, the complete ScaleRL configuration still consistently performed the best overall.
Interesting.
It suggests the recipe's strength comes from the combination of all these parts working together to maintain stability and efficiency. Even if one component, like say the FP32 fix, doesn't seem to give a huge marginal gain in a simple 8B run, its role in preventing instability might be absolutely critical when you scale up to a massive MOE model. It's about the whole package.
The whole package. Okay, so the recipe is built. It seems robust. The ultimate test, though, has to be scaling it up for real. That massive 100,000 GPU hour run you mentioned.
Yeah.
How did ScaleRL perform there? Did the predictive framework hold up?
It absolutely did. That was the real proving ground. And the performance they saw in that huge run, it closely tracked the sigmoidal curve they had predicted by extrapolating from just the initial stages of training using their framework.
So the prediction actually worked at extreme scale.
Yes. It demonstrated that the sigmoidal model and the ScaleRL recipe together provided genuine predictive power, even out to hundreds of thousands of GPU hours. That's a huge step towards making RL scaling more scientific.
Fantastic. So with the framework validated at scale, they could then use it to systematically explore scaling along different dimensions. Let's talk about model size first. They compared their 8 billion parameter dense model to a much bigger 17B by 16 Scout mixture of experts model.
Right. And the scaling trends held true for the MOE model as well, following that predictable sigmoid curve. But the results were really definitive in terms of performance.
How so?
The larger MOE model achieved a significantly higher asymptotic performance ceiling. Its dollar value was 0.710 compared to the 8B dense model, which plateaued around ablate 6 cents.
It's a much higher potential capability.
Exactly. And here's the kicker. The MOE model reached this higher ceiling using only about 1/6 of the total RL training compute that the smaller dense model consumed.
Wow, 1/6 the compute for a higher ceiling.
Yeah. It's pretty compelling evidence that investing in model scale, the architecture itself, is one of the most powerful ways to raise that fundamental performance ceiling, $8 in RL, just like in pre-training.
Okay, so bigger models, or maybe smarter architectures like MOE, raise $8. What about scaling the task itself? They looked at generation length, right? Comparing 14,000 token context versus 34,000.
They did, and this revealed a clear trade-off. Using the much longer context, the 34K tokens, it actually reduced efficiency early on. Your bar value was lower, D-billers was higher. It took longer to get going because the model was processing so much more information per step.
Slower acceleration.
Right, but it consistently resulted in a higher final asymptote, a higher dollar. The 34K run hit in a dollar of 0.645, whereas the 14K run capped out at 0.610.
So longer context hurts efficiency, but ultimately unlocks better performance.
That seems to be the conclusion. It validates that if you really want to push the absolute capability ceiling, especially for tasks needing long-range reasoning, you might need to invest in longer context RL, even if it costs you some speed early in training. It's another A-raising knob, but with an efficiency trade-off.
Okay, and the last scaling axis they looked at, global batch size, seemed to perfectly illustrate that bitter lesson concept in RL. What happened when they scaled up the number of prompts processed at once?
Yeah, this was a classic result confirmed at scale. When they used smaller batch sizes, the training looked really good initially. Very efficient gains, steep curve right at the start. It seemed promising.
Faster initial progress.
Exactly. But those runs tended to stagnate later on. The runs using much larger batch sizes, like 2048 prompts simultaneously, while maybe a bit slower out of the gate, they reliably avoided that downstream stagnation and consistently settle at a significantly higher asymptotic performance ceiling again, hitting that ACE.6455 mark.
So more compute per step, bigger batch, leads to a better final result, even if it looks less efficient early on.
Precisely. It's the bitter lesson. Leveraging more compute, even if it seems brute force via larger batches, often unlocks higher ultimate performance. You sacrifice some initial speed for a higher peak.
And this whole ScaleRL methodology wasn't just tied to one specific task, was it? Did it generalize?
It seemed to. They did experiments with multitask scaling, training the model jointly on both math problems and coding tasks. And the results showed these nice, clean, parallel sigmoidal scaling trends for each domain independently.
So you could track progress on math and code separately using the same framework.
Exactly. It suggests ScaleRL provides a stable and predictable foundation for managing even complex, multi-objective fine-tuning scenarios.
Okay, this is really quite comprehensive. It feels like a foundational piece of work for RL in the LLM era. It gives us both the scientific framework, the sigmoid curves for analysis, and a practical, tested recipe, ScaleRL. That seems very robust.
Absolutely.
For anyone out there actually training these models, the big takeaway seems to be knowing where to focus your engineering effort, right? It's about the off-policy algorithm setup like pipeline RL, getting the loss function right, CISPO looked really strong, and nailing down numerical stability with things like FP32 precision.
That's right. Because those are the decisions that fundamentally determine your performance ceiling, your $8. Get those wrong, and no amount of efficiency tuning might get you to the performance level you need.
It feels like it moves RL training at least a step away from pure guesswork or folklore towards actual engineering. Now you can potentially forecast your compute budget for a target performance.
And maybe even know if that target is achievable at all with your current setup before you spend those million GPU hours.
Right. But okay, if we can now predict RL scaling within a given setup, what's the next big frontier? Where does the research need to go now?
Well, the huge remaining challenge, the really big unknown, is how to connect the dots across the different stages of model development. Can we find predictive scaling laws that span everything, from the amount of pre-training compute to the model size and architecture, and then connect that to the RL training data quality and the compute spent using something like ScaleRL?
So predicting the entire pipeline's outcome based on the resources allocated to each stage.
Exactly. The massive question now is, what's the optimal way to allocate your total compute budget between pre-training and RL fine-tuning? How do you balance those phases to get the best possible final model, maximizing its overall capability and generalizability? That's where the next big breakthrough in scaling AI probably lies.
Finding that perfect balance, a fascinating challenge for the future.